So I'm from Ukraine, and now I am a postdoc in Spain, in Basque Country, and this is University of Basque Country, where this work was done. And before starting, I must sorry for my not good English. And so my talk is somehow related to the talk of yesterday of Aurel Gavrish. It's about non-unitary Grover algorithm. So here the same ideas used. And maybe somehow it's related to the previous talk, some non-unitary quantum processes. So let us remind something about quantum control and the tasks which solved by quantum control people. So if we have some initial state of the quantum system and we want to prepare somehow output quantum state, then we can apply or make the quantum system evolve by going it by some time-dependent Hamiltonian, for example, with external fields, time dependence of these external fields, and we can also apply some measurements on the system or the parts of the system, and thus our quantum process will be not unitary, but it can go to some interesting results. So let us remind about quantum evolution and so quantum process. They can be unitary. So if we have a closed system and the quantum system evolved by Schrödinger equation, and we have a purity or entropy, it's a constant here, and we have some non-unitary processes, which can be an interaction with environment, some measurements, and so on. And in such kind of processes, our purity or entropy of the system can change. It can dephasing. So if we have increasing of entropy or a distillation, if we have initially mixed state, we can make it, we can transform it to pure state. So the purity in such kind of processes can be constant or can be not constant. So we have a big variety. So in our problem, we look at the spin chain. It's a simple XY model, which can be solved analytically, but this is not the case, and we are interested in some other things. So we study closed spin chain with this Hamiltonian antiferromagnetic. And this is just a picture. We have some 6 spins. And now we make some modifications of this setup, and we add another external spin, which is coupled to one of the spin in this chain. So this is a locally coupled to one of the spin, and we always assume that the spin in chain, which is coupled to this probe spin, is spin number 1. And then the total Hamiltonian of the whole system is written here. So this is a spin chain part, and this is a coupling between this additional spin and the spin of the chain. So this is the same as we have here, so xy. And this is G is a coupling constant. So here coupling constant is 1, and here G can be different. So, and our algorithm is the following. So we start from a separate state. So we have a probe spin in the state spin up and some state of this spin chain. And then we evolve, so this total joint system evolves some evolution time tau. And so we have entanglement between this probe spin and the chain. And after this time tau, we have a measurement of this probe spin, and we have a selective measurement, and we check if the spin in a state spin up. If measurement say yes, so we continue. We again make the system evolve time tau and make this projective measurement again. And if the result of the measurement is spin down, we just reject the system and start again. This is a usual scenario of such kind of problems. So we are interested in the state of the spin chain, and we can, most of the talk, I will assume that the initial state of the chain is a pure state. So, but so this initial state of the chain, and after m times of iteration, the state can be written as follows. So this is m times v acting of operator v. So v is a non-unitary operator, and it can be written as follows. So this is a evolution of the joint system probe and chain, and this is a projection on a probe in a probe space. So this operator acting in a Hilbert space of the chain, because we trace it out this probe. And so this is what we do with this operator of our projective measurements. And of course, we have a probability to make this projective measurement successful. And this probability of measurement number J is the following. And the probability to have successful M sequential steps is the following. This is just a product of this P, P1, P2, and so on, and Pm. And it can be written as follows. So in the limit, when we have a Zeno-like regime, so this is like in previous talk, it was a Zeno regime. So we have also a Zeno-like regime. When the frequency of our selective measurement is very high, and this time period between two subsequent measurements goes to 0, we can rewrite, so we can assume that we have some non-Hermitian Hamiltonian acting in a subspace, acting in a Hilbert space of the chain. And after simple mathematics, we can write this non-Hermitian Hamiltonian in the following form. So this is initial Hamiltonian of spin chain without any additional parts, without probe. And this is additional terms. So we see that this is a non-Hermitian term because this is imaginary. And it looks like we have an imaginary local magnetic field acting on a spin number 1. And so, again, we can rewrite this Hamiltonian in the following form, where we write this. So this is just identity matrix, and we can combine this part and this into this term, which is just a projection to a spin down. So this is mathematical details. We just have some kind of I thought how to say it in English. So it's easy to see that our Hamiltonian will be in this form. So yeah. So I rewrite here this Hamiltonian again, and we can see. So we can deal with this non-Hermitian Hamiltonian like as usual we deal with Hermitian Hamiltonian, and the evolution of quantum state can be written as follows. So this is some exponential minus I eigenstates of this non-Hermitian Hamiltonian, and this is eigenvectors of this non-Hermitian Hamiltonian. But the problem is that so now this eigenenergies of this Hamiltonian in general are not real. So they have the imaginary part. But as we will see, not of them. So due to the form of this non-Hermitian part, we see that imaginary part of this eigen energies are always less or equal 0. And if we look to this formula with evolution of the state, we see that if imaginary part of this eigenvalue is non-zero, so less than 0, then we have exponential damping, and the norm of this vector is not conserved, and for some lambdas and for corresponded alphas, so for corresponded eigenvectors, we have decay, exponential decay. So we can assume that the total Hilbert space of the chain can be divided into two subspaces, decaying and non-decaying. So decaying space is when imaginary part of eigenvalue is non-zero, so less than 0. And non-decaying subspace is spanned by eigenvectors with corresponding eigenvalues where imaginary part is equal to 0. So they will not decay in our processes. So if we have initial state, any initial state, it can be decomposed into like a superposition of two vectors. A vector is lying in a decaying subspace, and vector is lying in non-decaying subspace. And after our non-unitary process, we will finish only with this part, with this part which is lying in non-decaying subspace. And the probability to reach this state, so after infinite number of measurements, so I will call it infinite process, is just square of this coefficient. And if we take some initial random state in the Hilbert space of the chain, so the average probability, average survival probability will be a fraction. So it is a dimension of a non-decaying subspace divided to dimension of total dimension of the Hilbert space of the chain. So I will not talk about this, but the main conclusion we can easily see from the Hamiltonian, so from this effective non-Hermitian Hamiltonian, is that the dimension of this non-decaying subspace does not depend of this coupling strength J and time interval tau. Of course, just in the limit when tau is going to 0. So we can ask a question: what happens with this dimension of non-decaying subspace? How it depends on the number of spins in spin chain. It is we can see it numerically because it is easy to find dimension of non-decaying subspace for reasonable number of spins. And we can see that this dimension of non-decaying subspace has this form for odd numbers of spin and even numbers of spins in the chain. And you can see that this is proportional to 2 in the power of n divided by 2. And turning back to this expression, we must divide it to the total dimension of a spin chain, which is 2 in the power of n. So we have the conclusion that average survival probability is proportional to the so exponentially decay with increasing of number of spins in the chain. So we can again when we see to this Hamiltonian, we can easily see that the form of the states in a non-decaying subspace is the following. We have a separated spin number 1 and some other state of the other spin in the chain. So we can call this highly localized spin Polaron because we have.
Pavlo, last 1 minute before we.
Okay.
Yeah.
So this is just a simple example. If we start with initial state of the chain, which is a ground state of the spin chain, plus all spins are up with some coefficient, then after applying our process, we finish with this states are up. So we have some kind of distillation. And we can make it by using only a local coupling and local spin measurement. So if we have some ensemble of random initial states, we can see that, and we can write a magnetization for different spin in chain. So we can see that magnetization of the first spin, which is coupled to the probe, becomes close to 1. And even if we switch off the probe, the state will be stable because this is an eigenstate of the total system.
We are 1 minute past your time. If we can just wrap up in the next minute or so, we can stick with the program.
Okay. So just finally remark, and if we start with a mixed state, which is composed from 2 different vectors from with the classical probabilities to be in a non-decaying subspace and in decaying subspace, then after applying our protocol, we can purify, so we can transform a mixed state to a pure state, which is lying in the non-decaying subspace. So this is conclusions. So I can say thank you for your attention.